Ravi कहाँ है? There. Najam, who should be on mute? I go on mute. No, I think you put yours on this thing. I unmute? Yeah, we'll. Okay. Then you can put on your video also. Because it takes the video of the person who's speaking. Huh. So video is also on. Slightly lower. This visible? Yeah. Okay. Yeah, already live stream. All right. Start. Okay, should I? Yeah. Okay. Okay. Morning. So this is the last lecture. And today, as I promised yesterday, today we would talk about recycled pulsars on the other side of the spectrum. Very small spin period, small magnetic field. Okay. So let us try and see how we can go there. Some of you would be familiar with these objects. So there are a set of observational classes in which we divide all the observed neutron stars. And the first one is, of course, radio pulsar. We have talked about the radio pulsars yesterday in some detail, so I would not repeat that. Then these are also seen in X-ray binaries. And the two major classes are the high mass X-ray binary and the low mass X-ray binary. And the mass refers to the companion. So the mass of the companion is high. In this picture, which is an artist impression of a high mass X-ray binary. So this star is huge. It's a giant. And there is this little neutron star. Of course, the picture is not to scale. And it has a small accretion disk compared to the size of the star. And these function as X-ray pulsars. The mechanism of X-ray pulsation, the mechanism of energy generation is very different from what we have discussed yesterday, because now the material is being channeled, some material is being channeled to the neutron star from this huge star. Material is falling onto a neutron star, and that is giving rise to X-rays. And because of the strong magnetic field, that X-ray is being channeled in a beam, and again, the star is rotating, so you get X-ray pulses. So these are these function as X-ray pulsars, and they are in LMXPs. Then we have the low mass X-ray binaries. Again, material is falling onto the neutron star, and therefore X-rays are being generated. But here in the low mass X-ray binaries, because of the processing of the neutron stars, the magnetic field is very, very low, I mean, in astrophysical terms. And because of the low magnetic field, it cannot channel the material. So there are no, pulses. What you see are continuum X-ray emission, and sometimes what you see are X-ray bursts. So material falls onto the neutron star, it sort of collects there. And after a while, if enough material has been collected, it can undergo a nuclear flash. So suddenly that material, which is basically hydrogen plasma, it can undergo nuclear fusion and can give you X-ray flashes. So now the question to ask is, why do we have neutron stars with low magnetic field in low mass X-ray binaries and relatively higher magnetic field in high mass X-ray binaries? This has to do with the nature of these two binaries and also the generation of the millisecond pulsars. So the basic difference between high mass X-ray binary and low mass X-ray binaries, as I have said, the companion stars. And you may recall your basic astrophysics, or if you have taken the course, or because you are interested, you probably have studied a little bit. The more massive the star, the faster are their evolutionary time scale. So everything happens very fast for massive stars, and everything happens very slowly for low mass stars. So what happens is, in massive stars, the time scale is large, but also the rate of accretion, I mean, rate of mass transfer is also very large. So it transfers a lot of material to the neutron star in a very short time, and essentially buries the magnetic field under this material that is coming in. And therefore, the magnetic field does not, neither has the time nor the situation for the field to decay. So because of this situation, in high mass X-ray binaries, a very strong magnetic field is retained. Whereas in low mass X-ray binaries, everything is very slow, the rate of accretion is very small, but it's happening over a very long time and the magnetic field decays. Also, because of the very long time, the neutron star has enough time to acquire extra angular momentum, which spins it up. So therefore, a neutron star sitting in a low mass X-ray binary, what is happening to it is its magnetic field gets smaller. Also, its spin period gets shorter. And, those are the characteristics of the millisecond pulsars. Short period, low magnetic field, these are the objects. And of course, these are magnetars. We would not talk about them today. So these are the basic classes of rotation-powered pulsars. The classical radio pulsars, which we discussed yesterday, recycled radio pulsars. These are the objects which were sitting in a binary, and then when the accretion process stops, they again show up as radio pulsars. And so the millisecond pulsars, radio pulsars, come from the low mass X-ray binaries. And there is another set which we generally call mildly recycled pulsars. They have been recycled, but not too much. Those are the ones who come from the high mass X-ray binaries. And of course, we see them in the accreting phase as X-ray pulsars and this low magnetic field objects. Then there are internal energy objects, which we discussed yesterday, that they are neither supported by their spin down, nor any accretion is happening. They have some internal source of energy, like the magnetars, where the source is decay of the magnetic field. So these are the basic classes of neutron stars. And here is the BP diagram in its full glory. Many of you have seen this picture earlier, and we have everything that we see of neutron stars in this picture. So these are the regular radio pulsars, higher magnetic field, slower spin period. These are the objects that we were talking about yesterday. These are the magnetars. These are the millisecond pulsars. These fellows there, these are the X-ray pulsars sitting in high mass X-ray binaries. So that's the whole menagerie of neutron stars. And you will notice that there are these huge lines, pink lines here. These are not error bars, but uncertainty in measurement. Not errors, but huge uncertainty in measurement. So this is roughly the picture. And today we would basically concentrate upon these fellows. So what are the evolutionary pathways? Please remember that we kept on saying, I go back to this, that these fellows would slow down because radiation is going out, taking away rotational energy. So they would move towards the right and cross the death line and would not be visible to us. So that's what happens. So these are the pulsars which slow down, cross the death line, and become dead pulsars, which we do not see. Okay. So now, If that was the only thing that was happening, we should have had a bunch of radio pulsars and then they slow down and go away. But if I plot the spin period histogram, this is what we see. And you can clearly see various other things are there. Most importantly, there is the main histogram, the main Gaussian-like curve for the ordinary pulsars, and this one is obviously for the millisecond pulsars. From the value of the spin period, you can see that clearly. Now, so there is a small thing there, which is the not the magnetas. Magnetas have not been plotted in this picture. These are the newly discovered long period pulsars. So they are, sorry. So they are showing up as perhaps a different population, but these are the very, very long period pulsars, and these are our millisecond pulsars. So as I have said that we have recycling, and this is the millisecond pulsars which are coming through via low mass X-ray binaries. But if you look at this histogram clearly, you see another small histogram sitting there. Okay, and this one has slightly larger spin period, and if you go to the BP diagram, you'll see that they also have a slightly higher magnetic field. These are the mildly recycled pulsars. Okay, so one of the important issues about recycling is the spin-up line. You see here are this is again, some schematic version of the spin period magnetic field diagram. This is B and this is P. So here are the normal pulsars. They would have died, but because of recycling, they are coming up. And there is a limit to how much they can be spun up. And it is intimately tied to the final magnetic field that they have. So in any of these systems, when the material accretes onto the neutron star, depending on the model of your magnetic field, you can do evolutionary calculation. You can, let the magnetic field evolve over time. And what happens is, because of the nature of accretion and the interior of the neutron star, the magnetic field saturates at a point. It does not go on decaying indefinitely. So it would saturate at some value, depending on the model parameters and of course the rate of accretion and various other things. Now, given that final value of the magnetic field, there is a limit as to how much you can spin it up. You cannot spin it up indefinitely. You cannot say that, okay, I have a low mass X-ray binary which is going on for billions of years, and a neutron star is there, and I will spin it up to whatever. You cannot do that. Okay, so depending on the magnetic field and the rate of accretion, there is a limit to how much you can spin it up. And that limit is shown by this line, which is called the spin-up line. So all the millisecond pulsars that you are able to generate, they would be generated below the spin-up line. Spin-up line is kind of the limit to which you can take it by the method of recycling. Now, this particular concept is very important for the problem that we would be looking at today. Okay, so this is proper demonstration of the spin-up line. So here is the MSRP spin-up line, and now you can see that when I plot this spin-up line with the data, nothing is above the spin-up line. So that's absolutely the limit. And this is our old friend, the death line that we were talking about yesterday. That's rotation powered pulsars, radio pulsars, basically. Yeah. All right. So schematically, this is what is happening to the neutron stars. These fellows are slowing down and they are going here, which we are seeing in the HMXBs. In LMXBs, we don't really see them, but they would go to some regions like that. Then if they are sitting in LMXBs, they will take a path like this. We do not know. We can only theoretically sort of guess. And they would appear here as millisecond pulsars. And if they are sitting in HMXBs, they would end up here, slightly, mildly recycled pulsars. So that's our picture. And this is the summary of radio pulsar recycling. So if they are, yes. This picture, this one has about 4,000 objects. So, and mostly here, of course, this orange place. Okay, so in summary, so we have solitary pulsars, which have a magnetic field of about 10 power 11 to 10 power 13. I should modify this slide. As we have seen yesterday, the numbers have been pushed to about 10 power 16 now. So from high mass extra binaries, we have high mass binary pulsars. And the companions, we have massive companions, masses more than at least half a solar mass. And the final magnetic field is about more than 10 to the power 10 Gauss, at least. In comparison, the low mass extra binaries will get low mass binary pulsars and also solitary pulsars. And the companions are low mass stars, less than about half a solar mass, typically white dwarfs. And the field is now about from 10 to the power 7 to 10 power 10 Gauss. Okay. Now, we have the recycled pulsars. So we had the stars which died and became neutron stars. And now they became radio pulsars and they cross the death line. So they become dead pulsars. We have recycled them and given them a new life. And now we are again talking about the death line of these reborn pulsars. So life and death continuously. All right. So here is a picture. So this is my spin-up line. This is the parameters were not correct. So you see two of them sticking above the spin-up line, which is not correct. And you will see that even among the millisecond pulsars, there are various subclasses. And what I have shown here are millisecond pulsars in the galactic disk, millisecond pulsars in the globular clusters, and isolated and binary by two different symbols. And it appears that there are these subclasses and some more, which have somewhat different kind of properties. And these people have been looking at these subclasses and the properties for some time, and we are hoping that the paper would come out soon. I mean, we'll be able to submit it soon. They presented it in ASI 2022, that's last year, but we are still getting everything correct. Okay, so now, if you look at the this picture a little more carefully, what you see is this death line. Let me tell you, this death line is also, this is an older picture. So yesterday I was showing two death lines. So this is the upper death line. See, quite a few below that. So now we sort of use the lower death line more. But qualitatively, this is the death line. And you will see that in this region, lot of stars are here and sort of hugging the death line. So this qualitatively gives you the death line correct, slightly low. In the case of the millisecond pulsars, you see the population is reasonably above the death line. Then the question is, the recycling is happening via this region, right? Okay. And if they can move like this, and if the death line is here, why aren't we seeing many objects in this region? That is a question. I mean, that region, we should have some objects in that region. And it's very, very clear that we are not seeing something there. So is this death line, or, something similar to that, the physics that we are using to make this death line, is it valid for millisecond pulsars also? That is the question. Because you can see that millisecond pulsars are somewhat different from the firstborn pulsars. Right? They have gone through all this churning in the X-ray binaries. A lot of things has happened to it. So they are somewhat different. So using the same physics, the same argument to draw a death line, is it correct? Now, this question has been kind of going around in people's discussion conferences and so on, and nobody really did anything about it till last year. This is a Russian group again, and last year they put out 2 papers in a series talking about the death line and saying that the death line has a break. Look at their death line. They have given, again, they have given 2 death lines using 2 different sets of parameters. And you see that in the upper region, this is the line, and in the lower region, the slope has changed. Okay. And exactly what we were seeing in the earlier picture, we really need a line like this, right, with a different slope, which will hug the population. And exactly that is what they have done. And so what they have done, they have again taken, last night we were discussing, and there is this little controversy between various groups about the definition of millisecond pulsars. The standard definition of millisecond pulsars is pulsars with spin period less than 20 or 30 milliseconds. And there are some people do not agree with that. So I went from 20 millisecond to 30 millisecond, and some people believe that 30 is not correct. And we may also revise our opinion, and all that is happening. But in this particular paper, they have put the break at about 0.3 seconds. So about, this is 30 milliseconds. So that's where they are putting the break. And they're saying that the nature of the magnetic field changes for the millisecond pulsars. And therefore, while defining the death line, the slope should change around that value. Okay? Now.
No correction. Beskin without G.
Huh?
Beskin without G.
Sorry. This must have been an auto. Yeah. I'm sorry. Yeah, Beskin. Beskin, yes. So please note that Beskin without G. The G is, it's a misspelling. That there shouldn't be a G. Huh? Very good paper. Yeah, I know. Very good paper. So I totally agree with this paper, the philosophy of this paper, but I have a different way of looking at it. And that's what I will tell you. So, okay. Looks like we'll finish much earlier than expected. Okay. So here, this work specifically assumes a different kind of magnetic field configuration. So, which is a very sensible and reasonable assumption, because the nature of the magnetic field is likely to change, the field configuration. As I have discussed yesterday, that we assume a purely dipolar field for the ease of calculation. The more complex the magnetic field we take, our life becomes difficult. The calculations become difficult. But in reality, individual pulsars have been investigated, and there are clear evidence of magnetic field having much more complex structure configuration compared to dipolar field. So therefore, such a complex configuration, when it goes through a massive process like material accretion, that field configuration is obviously going to change very complex way, and therefore the final field configuration would also be very, very different. So what they have done, they have looked at various field configurations and have figured out what is the field configuration that gives this kind of break in the death line. So they have looked at the data, and they have tried to figure out a field configuration that gives the required kind of death line. So that's their way of doing it. I am trying to look at it in a different fashion. What I am trying to do is, I am saying that I really do not know about the field structure. And I am not going to make an assumption about the field structure, because it's very difficult to figure out what kind of field structure initially was and what it changed to. What I am going to say is, instead, there are things that I know about the accretion process. In other words, we know the range of accretion rate that comes from the nature of the X-ray binaries. So we know the rates of the accretion rates, and we also know the range of final magnetic fields, right? That also comes from our model, which matches to the observation. So depending on the rate of accretion and the magnetic field, this is what we created, the spin-up line. Okay. Now, this spin-up line, you have to see from, you must understand from this picture that this must be a limiting line. No millisecond pulses above that. So what is the parameter that is controlling this? The parameter that controls this is the rate of accretion. Now, every object has one rate of accretion, which is the maximum rate of accretion. You cannot dump material onto an object at a rate faster than that. And that is called the Eddington rate of accretion. Now the question is, why can I not do this? Suppose I have some mechanism, I keep dumping material onto something. What limits that? The physics that limits it is that as I am dumping material onto an object, as you know, the material falls onto this compact object, and we have done this problem millions of times from our school life. A body falls from a height to the surface of anything, even on Earth. It loses potential energy that gets converted to kinetic energy, and that's what is giving rise to the X-rays. Okay, so if you are throwing material onto a neutron star, because the change in the potential energy is so much, it gives rise to X-rays, and these X-rays are coming out, and this X-rays has pressure. So then that would resist material to fall onto it. Every radiation has pressure, right? So radiation pressure. So therefore, there reaches a point that the radiation pressure becomes so much, it stops the material from falling in. So, yes? Polar cap, if the accretion is the channelized accretion, it may also happen all over the surface, but let us talk about the polar cap accretion. Yes.
That case, it will be a hurdle to material falling on that.
So the material is trying to fall onto the polar cap, and accretion is coming out from the polar cap. So it will resist the material. So independent of whether the material is falling all over the surface or on the polar cap, the same mechanism would happen. So this defines a limit to the accretion rate. And this is called the Eddington rate of accretion. I'm sorry. And this is called the Eddington rate of accretion, which is about 10 to the power minus 8 solar masses per year for a neutron star. Okay. Now we can do this calculation. I mean, this is a good calculation that you can do just to understand the process. So you cannot have an accretion rate onto the neutron star larger than the Eddington rate of accretion. Okay. And that is what has been used to calculate this spin-up line. All right? Okay. Now, we have seen many systems now. There are objects called accreting millisecond pulsars. Millisecond pulsars, but they're still accreting. So the accretion phase is about to get over, but hasn't yet happened. And actually, we have seen systems, I think there are now 6 such systems. They are sputtering. The accretion is sputtering. It's almost getting over. So sometimes the accretion goes away and this object shows up as radio pulsar, but sometimes the accretion comes back, it shows up at accreting millisecond pulsar. Okay, so very clearly that this is ending the phase of accretion. And in such systems, what we have seen is that the rate of accretion is much lower. If the rate of accretion is lower, then this spin-up line would move, right? Because this line has been calculated using Eddington rate of accretion. If my rate of accretion is lower, this line would move. And the slope of this line is proportional to m dot, the rate of accretion. Okay, so now see the magic. This is the break that we are talking about. This is the same picture, slightly enlarged. I have drawn another line here. This line I have drawn not looking at the data, but by making it parallel to this spin-up line. So basically what I have done, I have taken a line which is parallel to this, which means everything remains the same. I am changing the rate of accretion here. And I move it and try to see if I can have a line which can function as a death line to the millisecond pulsars. And you see that that can happen. So therefore, my conjecture is that if we can figure out the conditions for this line, this is done without going into the numbers. But we can see that we have a death line-like thing, some line, which can function as a death line for the millisecond pulsars, which is essentially a spin-up line. It's not a death line. It's actually a spin-up line. This was my original death line. this black one. That was my original deathline. And which we said that, this is not really functioning for the millisecond pulsars. And this one seems to work very well for the millisecond pulsar. The break is coming closer to 0.3, not really 0.3, slightly below that. One can look at these numbers, but this looks very similar to the kind of thing that Beskin and Litvinov had suggested. So we are arriving at a very similar conclusion, going from taking a different path. Okay. So the problem and now is, this is a conjecture. To put all these numbers, to run the magnetic field evolution calculations and see whether this works. So that is the problem, the second problem that I wanted to talk about. And that's all I really have to say about this. Thank you very much. And that's it.
Questions?
This new spin-up line is interesting.
Mm.
The red line. Would it affect by Eddington rate of acceleration by?
No, Eddington rate of accretion is given by the mass and the radius of the neutron star, the compactness of the neutron star. That is defined. All one is saying is every system is not accreting at Eddington rate. That's an upper limit.
That is the upper limit. So there can be the lower limit of the constant.
What constants? That is the crux of the problem. What sets this limit? Whether there is a mechanism in the magnetic field evolution and the nature of the accretion in the interaction of the system that sets this accretion rate and the field evolution, the final field configurations. Because what we are seeing here, we see that if we can shift the spin-up line a little bit downwards, that fits the death line. But how do you get to it?
Yeah, but what regulates the depth of the signal? How deep or how high?
That's what one needs to.
You can put it anywhere, just like that. Yeah.
No, arbitrarily you can put it anywhere. The fact is, this seems to be matching our requirement. Now, why is it matching our requirement? It has to come from the physics of the field evolution and the rate of accretion and so on. So we have to now go back to the field evolution scenario and the interaction between in an LMXB to see what are the rates of accretion and how actually the data would come from the AMXPs, the accreting millisecond X-ray pulsars, what kind of accretion rate they are finally saturating to, and whether that is defining this line.
And what do you do? Some of them sticking out too.
So some of them would always stick out. So you can't really fit the entire. There would always be a few which would go below, and if there are only a few, then maybe.
There's a deadline and then few. That means they like.
So you have to see how many are below. See, in this case, if you see that see the death line, there. Sorry. There are about 2 or 3. Now, this line that I have drawn, this is completely looking at it. Okay, so no calculation has gone into this death line. So what I'm saying is this line has to now be produced by calculation. That's the problem. That's the task, to generate this line by proper calculation. Any other question?
Possible scenario, like according to you, for that intersection,
Which intersection?
that this kind of time meets.
You mean
They
what?
need- they need-
The knee. The knee is the process of recycling. You have the unrecycled objects on one side and you have the recycled objects on another side. So that is the physics which is giving rise to the knee. The exact location of the knee would there cannot be a very sharp location of the knee. We may theoretically say there is a knee, but it should be a region, no? Because there will be some firstborn objects on this side, some recycled objects on that side. Nature is not sharp, but theoretically that's what we do. Okay, thank you. If there are no further questions, then we